Well, I'd like to welcome everyone to our webinar today. The title of the webinar, Successful Phosphorus Removal. My name is Kevin Cope. I'm in business development for Brenntag North America. I will be the host, and a gentleman named Sean Heyer, who I will introduce shortly, will be our presenter. If you look on your screen, you will notice somewhere on your screen an orange arrow. If you click that orange arrow, it should expand a box that looks somewhat similar to this. And if you look lower, you will see an area where you can type in a question. So if you have a question, please type in your question there, then hit send or submit. And if possible, during the webinar, Sean or myself will answer the question. If we don't get to your question, we will be able to, that question will show up on our files later, and we will respond after the webinar. So, and then to simply minimize this, just simply click the orange button, and that'll go away. In the past, Brenntag has done a number of webinars: heavy metals removal, anti-scalants, oily waste treatment, foam control, which was sponsored in part by the AWT, Association of Water Technologies, coagulation flocculation, successful jar testing, and successful plant trials. Many of these are available in video forms, and all are available in PDF forms. So if there are other trainings you would like to see from Brenntag, please reach out to me, and my address and phone number will be at the end of the presentation, and we can supply you either the PDF version or, if possible, a link to the video. Our presentation today is called Successful Phosphorus Removal. And I'm very proud to introduce Sean Heyer. Sean is a member of Brenntag Mid-South. Sean has served in the Navy for 4 years, and Sean, I'd like to personally thank you for the service. Sean currently holds a BS in biology from the University of Kansas. He was a KCMO water plant laboratory technician. He's a pre-treatment coordinator for Johnson County, Kansas. His experience includes the power industry, power chemicals, being with G.C. Robbins and Brenntag for the last 18 years. He's married for 30 years to his wife, Lynn, who I believe is actually listening today, so welcome, Lynn, with 3 boys, Max, PJ, and Ben. And Sean's hobbies include golf, travel, backpacking, and working old cars. So, Sean, I will turn it over to you, and let us begin.
Okay, thanks, Kevin. I appreciate it. Today we are going to talk about phosphorus removal in wastewater treatment. What I'd like to cover today is the reasons why we need to remove phosphorus, sources of phosphorus in waterways and wastewater, regulations regarding phosphorus, the actual phosphorus removal in wastewater treatment, how we test for phosphorus removal, and then safety. So, definition: phosphate indicates the fully oxidized acid salts of the element phosphorus. Why do we say phosphate or phosphorus? This is because elemental phosphorus never occurs by itself in water, but is always as some type of compound, and typically phosphate. I'll cover that a little bit in more detail a little bit later in the presentation. Next. So phosphorus, it's an element prevalent in many compounds in nature. It's a key nutrient for the growth of plants, including crops. And as a result, phosphorus is being used in large quantities as a fertilizer. It's on an industrial scale as well as in many households. So phosphorus management is of extreme importance. Next. So why do we need to remove phosphorus? Phosphorus is one of 2 nutrients of concern in water, the other being total nitrogen. Ammonia, part of nitrogen, exerts a BOD and can be toxic to many fish in amounts as low as 0.02 milligrams per liter. And discharging wastewater with excess nutrients can contribute to excess algae growth, which in turn can lead to eutrophication. Next. So eutrophication, here's a definition. Basically, eutrophication is a deterioration of water quality due primarily to excess algae growth. Algae blooms in the presence of nitrogen and phosphorus. These blooms block the sunlight, The algae eventually decays, settles to the bottom of the lake, and rots. The decay of the algae and other microorganisms depletes the oxygen in the water. This can produce dead zones and can lead to permanent ecosystem damage. Of the two nutrients, phosphorus is considered the limiting nutrient, as there are other sources of nitrogen. Next. So sources of phosphorus to the environment. About 66% of phosphorus is from fertilization of croplands and livestock operations and their associated runoff. And 33% comes from municipal and industrial wastewater discharges, urban runoff, stream bank erosion, and seepage from septic tanks. Today, I'm going to focus on the treatment of municipal wastewater discharges. Next. So sources of phosphorus in wastewater, these come from laundry and dish detergents, boiler and cooling tower discharges, food and drink. Look this up online. Some foods that contain phosphorus are nuts, almonds and pine nuts, fish, salmon, mackerel, and carp. I was kind of surprised to see that carp made the food list. However, if you'd like some carp, I know a restaurant in Omaha, Nebraska called Joe Tessa's, where you can try some carp. Also comes from I&I infiltration into collection systems. This infiltrate may contain leached nutrients, especially from fertilizers. And then others, including industrial discharges discharges from food production plants and industries, phosphatized metals, and others. Next. So regulatory limits. Right now, the U.S. EPA currently has no federal standard for nutrient discharge limits. Some states are requiring the POTWs to monitor ammonia, nitrate, and phosphorus in their discharge. In addition, some states have already adopted numeric limits for nutrients. The standards are very dependent on the quantity and quality of the receiving stream. The Chesapeake Bay would be one example of a receiving stream with numeric nutrient limits. Next. I'm from Kansas City, Missouri, so I'm more familiar with the regulations that apply to Missouri and Kansas. In 2014, the Missouri Department of Natural Resources proposed a nutrient reduction plan. This was for the wastewater treatment plants with a discharge of greater than 1 million gallons a day. The plan recommended monthly monitoring for ammonia and phosphorus. Currently, plants with discharge more than 100,000 gallons a day are required to monitor for total nitrogen and phosphorus on a quarterly basis. And then the only plants with a permit limit for phosphorus are located within the Taneycomo and Table Rock Lake watersheds. At this time, not all the dischargers within these watersheds have permit limits, but a phosphorus limit is contained in all new permits. The current limits for phosphorus were determined by waste load allocation to the watersheds. These were based on dissolved oxygen directly attributable to nutrient modeling. Missouri is currently in the process of developing new criteria for nutrient discharge limitations. In the state of Kansas, the discharge limits are dependent upon a couple of factors. The health of the receiving stream, when the permit was written. As new permits are written, numeric limits on nutrients are put in place. Kansas is now also working with permittees for limits on the gross amount of nutrients being discharged. So, for example, a new permit limit may be 10 parts per million for total nitrogen and 1 part per million for total phosphorus, or 8 parts per million for nitrogen and 1.5 parts per million for total phosphorus. This is, based on total daily maximum loads and the fact that a plant may be better at removing one nutrient more than the other. with this type of permanent limit, the total nutrient discharge is regarded more so than each nutrient individually. Next. So here's a map of the United States with some states in colors. These are states that have discharge concern areas for phosphorus. You can see on the eastern seaboard, the Chesapeake Bay is one of those areas. Next. So I was talking about 1 part per million limit for phosphorus. So just to give you an idea, if you to think about the small quantity that we're talking about, here's a slide of a 1 gallon of water. And this is that same gallon of water in a 1,000,000-gallon tank. So you can see a very small limit, and actually limits are even smaller than that. So phosphorus removal, very important in getting down to very negligible levels. Next. So how is phosphorus removal achieved in wastewater treatment? Typically, raw wastewater entering a wastewater treatment plant is approximately 2/3 soluble or dissolved, and 1/3 particulate or insoluble. The key to effectively treating phosphorus is to convert all of the soluble phosphorus to the particulate form for settling and filtering. Two main types of treatment for phosphorus treatment are biological and chemical. I'm first going to cover the biological treatment. If you're treating phosphorus biologically, then you're also treating for BOD and ammonia. So I'm going to give an overview of an activated sludge process that would be designed for BOD, ammonia, and possibly phosphorus removal. Next. Okay, so there's many variations to the activated sludge process that I'm going to describe. I think it's important that we understand the treatment processes so that we can know the nutrient removal capabilities, specifically phosphorus in our conversation today. So BOD removal is the main treatment stage in all municipal wastewater treatment plants. BOD reduction is achieved by microorganisms processing the wastewater. These microorganisms basically need carbon, as do all living organisms, and oxygen for growth. So the microorganisms, in this case, in basically secondary treatment, use organic compounds in the wastewater as their carbon source and break down the BOD. And by breakdown, I mean they convert the organic nitrogen to ammonia, water, and carbon dioxide. Microorganisms now use the carbon dioxide from the breakdown of the BOD as their carbon source. These are called autotrophs. They're also called nitrifying organisms, and they convert the ammonia to nitrite and almost immediately to nitrate. These are slower growing and more sensitive to pH and temperature. So this process of converting ammonia to nitrate is called nitrification. And to achieve good nitrification, we must have good BOD removal, as the heterotrophs outcompete the autotrophs. Next. So here's a simple drawing of a plant. The BOD and ammonia are reduced to nitrate in the nitrification zone. The activated sludge is then discharged to the clarifier for settling. Some of the settled sludge is returned as returned activated sludge back to the effluent, while some of it is wasted. Next. Okay, so the last stage in ammonia removal is denitrification. This is a conversion of nitrate to nitrogen gas, which is then released into the atmosphere. This is important as nitrate is our main component in fertilizers. This is also accomplished by heterotrophic microorganisms, but without the presence of oxygen. This is called an anoxic process. No dissolved oxygen is present, so the bacteria now have to use the nitrate as their oxygen source. We can accomplish this in 2 stages. In the first stage of treatment, we aerate, reducing the BOD, converting ammonia to nitrate. Then we discharge to a second tank. In the second tank, we no longer aerate, but still mix to prevent settling. This can also be accomplished in one tank simply by turning off the aeration and reducing the dissolved oxygen. One issue with denitrification is very little organic carbon food is left for the heterotrophs, which were removed during the nitrification stage. So plants can put an anoxic zone at the front of the process and recycle their sludge containing the nitrates back to the front of the plant where there's plenty of organic carbon. Next. So here's an example of a system. In this system, percentage of the mixed liquor suspended solids from the nitrification stage is recycled back to an anoxic zone at the front of the plant for denitrification. Now, because there is some nitrate which flows from the aerobic zone through the system, a post-anoxic zone can also be added and followed by an aerobic zone to help remove any remaining BOD and ammonia. This four-stage treatment is called a Bardenfaux process and was developed back in 1971. The reason I'm using this as an example is because the faux in Bardenfaux is for phosphorus treatment. Next. So now we're going to take this a step further and discuss the biological process for phosphorus removal. As I said before, the key to effectively treating phosphorus is to convert all the soluble phosphorus to the insoluble form for settling and filtering. So biological removal processes are designed to cultivate microorganisms in the suspended solids or mixed liquor suspended solids that store phosphorus. Microorganisms can use a phosphorus compound called ATP, adenosine triphosphate, as an energy source. These types of bacteria are generally called phosphorus accumulating organisms, or PAOs. And the PAOs take up phosphorus in aerobic conditions, and they release phosphorus in anaerobic conditions. Difference between anaerobic and anoxic is anaerobic, there's no DO, and there's also no nitrate. Next. So you can see we took the Bardenfaux system before. Now we've added an anaerobic zone at the front. So by having the anaerobic process at the beginning of the treatment system, you're providing the microorganisms with an ample source of carbonaceous BOD, the organic ferment in the anaerobic zone, and create a source of volatile fatty acids, which serve as food for the PAOs. And so although they are releasing phosphorus under anaerobic conditions, they take up excess phosphorus during the aerobic stage. Next. So by repeating this cycle of aerobic and anaerobic conditions, the phosphorus accumulating organisms take up excess phosphorus. The phosphorus is then removed by wasting. This must be an activated sludge process, and biological treatment for phosphorus reduction is reliable to about 1 milligram per liter. Next. So here's a picture of one process. This has many cells in it. I believe this first stage they're aerating, and then as it moves on, there are different zones, or anoxic zones, anaerobic zones, so on. And a video showing some aeration going on. Okay, some issues that can happen. We can have upset conditions with the biological process, such as hydraulic overloading or slug discharges. The plants need to have a proper ratio of BOD to phosphorus. There can be insufficient volatile fatty acids. As I said before, it has to be an activated sludge process for good phosphorus removal. This can't be accomplished with a fixed film process like trickling filters or rotating biological contactors. And you need a large enough footprint for all the tankage and detention times. Next. So, in addition to the biological treatment for the removal of phosphorus, phosphorus can also be removed chemically. Again, the key to effectively treating for phosphorus removal is to convert all the dissolved phosphorus to particulate form and then settle or filter. The chemical process involves the addition of a metal ion to the wastewater. The metals typically used for treatment are calcium in the form of lime, aluminum in the form of aluminum sulfate, sodium aluminate, polyaluminum chloride, and iron in the form of ferric chloride, ferric sulfate, and ferrous sulfate. So the metal ion bonds with the soluble phosphorus to form an insoluble metal phosphate. The metal phosphate can then be precipitated and filtered out. And chemical treatment of phosphorus is reliable to about 0.05 milligrams per liter. Next. So some chemical considerations. Phosphorus removal is more efficient in different pH ranges depending on the metal salt being used. As an example, in a low pH environment, sodium aluminate may be the best option as it will not decrease alkalinity like iron or aluminum sulfate and will actually raise the pH. Ferric and ferrous products may interfere with ultraviolet transmittance, UV, used for disinfection in some wastewater treatment plants. And then plants with primary and secondary clarification may treat at both stages, with the secondary acting as a polishing stage. This can also help with chemical feed efficiencies. Next. So jar test procedures for phosphorus removal. What the analyst wants to do is collect samples where you expect to treat chemically in the plant. Try and emulate plant conditions as closely as possible. This includes mixing energies, detention time, settling, filtration, etc. And the labware used in testing must be free of contaminants. Since some dishwashing solutions contain phosphate, the analyst has to be sure and clean the labware thoroughly. Recommended to clean with a mild hydrochloric acid solution and then rinse thoroughly prior to performing test. Next. So dosage determinations. Chemical addition can be calculated based on mole ratios. As an example, alum and iron basically have a 1-to-1 mole ratio with phosphorus down to about 1 part per million. So 1 mole of aluminum will form a bond with 1 mole of phosphorus. However, at this point, due to solubilities, the mole ratio increases and the amount of chemical required also increases. So it may be more effective to simply screen the chemical requirements by incremental addition, 5, 10, 15, 20 parts per million. Measure the results from testing and then test further based on the results from your initial testing. Next. So here's a video of our analyst. The analyst is placing the chemicals on septums, the little disc, so that they can be added at the same time and receive an equal amount of treatment time. In this video, we're seeing the beginning Stages of flock formation. That jar has some really good flock formation going on. And again, a topside view. You can see the flock particles in the water with the disc at the bottom there. And again, some really good flock formation in these last two jars. So chemical flock is formed by reacting the metal salt with the phosphorus. We want to make sure that it settles so that our effluent doesn't contain the insoluble phosphorus. We don't want any carryover. So here's a really good picture sequence of the treatment. We've got our water to be treated in the first picture. We've added the chemical in the second one and begin to form flock. In the third one, we can see that the water is starting to clarify. And in the last one, the flock is at the bottom and the water looks really clean. Next. So in some instances, filtration may be necessary. In this picture, the analyst is filtering a flock sample. Next. So once we've done the jar testing, we're going to want to perform our analysis for the phosphorus. There's 3 different tests for measuring phosphorus. And within each of these tests, you can measure for both particulate or dissolved phosphorus. So the 3 tests are orthophosphate, acid hydrolyzable phosphate, and total phosphorus. So only orthophosphate can be measured directly. The other forms must be digested in either an acid or an acid plus an oxidant to convert them to a measurable form of orthophosphate. So the state of Missouri and the state of Kansas require total phosphorus on their permits. So whenever you're doing reporting, digestion is necessary. Next. So it's important when discussing results from phosphorus from testing, we're clear about the form of phosphorus we're measuring. So was the sample digested? If not, then we know that we're talking about orthophosphate. So this brings me back to something I touched on a little bit earlier. Are we measuring phosphorus or phosphate? So orthophosphate can be displayed in 2 different ways. We'll see them on this little chart here. PO4 3- refers to orthophosphate. PO4 - P refers to orthophosphate as phosphorus. The difference between the 2 is important. The PO4 3- combines both the phosphorus and the oxygen, the phosphate compound, whereas the PO4 - P is talking about only the actual phosphorus. So if the sample was digested with an acid and potassium persulfate, then we're measuring total phosphorus. So for purposes of benchtop testing, an orthophosphate test may be all that's necessary. What you can do is run a total phosphorus and an orthophosphorus on a treated sample and check the ratio. If they're close to equal, then we know orthophosphate is a good measurement. If the orthophosphate is less than the total phosphorus, then running a digested sample may be necessary. Next. So here's a picture of some phosphorus testing equipment that I use in my lab. So the reactor on the left is used for digesting samples. On the right, this is the DR890 colorimeter I use for phosphorus testing. It can be used for both ortho and total phosphorus. The total, obviously, you need to run the digestion first. Next. So the test I use is called the ascorbic acid test. So this is also called the Phosphorus 3 test. The wastewater, treated wastewater is placed in 2 vials. Then you add a Phosphorous 3 phosphate powder pillow to one vial and swirl to dissolve the powder. And if you have phosphate present, a blue color will develop. Then set a timer for 2 minutes for a reaction to take place. The colorimeter is zeroed against the actual blank sample, and then the prepared sample is measured. Next. So for the total phosphorus test, you're first going to take a potassium persulfate powder pillow, add it to the sample, and swirl it to dissolve. A sulfuric acid solution is then added, and the sample is digested by boiling gently for 30 minutes. Sample is then cooled to room temperature. Sodium hydroxide solution is added to the digested sample, and the sample is returned to its original volume with deionized water. The sample is then tested with orthophosphate, the orthophosphate test method that I described earlier. Next. So here's a picture. This particular test for running total phosphorus requires a 25 ml sample. You can see that in the graduated cylinder. I've added the potassium persulfate pillow, and in the slide on the right, I'm adding some sulfuric acid. Next. And I'm doing the digestion here. Some people use a hot plate. I have a stove in my lab, so I just use the element on the stove for running my digestions. Next. So now the sample's been digested. So the first slide, I'm adding this sodium hydroxide solution, then bring it back up to its 25 ml with deionized water, and then go ahead and run the orthophosphate test. And so you can kind of see in this last picture, it says PO4 at the bottom. So this is measuring phosphate. This is going to include oxygen. On this particular colorimeter, I can hit a concentration button, and it will automatically do the conversion to the actual total phosphorus as phosphorus. If you don't have that, you can just simply multiply the result by 3.27, and that will give you your actual phosphorus. Next. So safety, very important. Obviously, there's a risk to health when working with any polluted material. Digestion solutions can contain high concentrations of sulfuric acid, so we want to make sure and use proper PPE. Some test methods also require mercuric sulfate solution, so precautions should be taken to eliminate mercury exposure to the analyst and the associated equipment. In this slide, I believe in the first one, the analyst is actually working underneath the hood. So use proper precautions such as working underneath the hood or whatever is prescribed when you're handling these products. Next. So in summary, phosphorus is necessary for the growth of organisms, but excessive amounts discharging into waterways can cause unwanted algae growth and lead to eutrophication. Phosphorus discharge limits, if not already in place, are imminent. Phosphorus can be treated both biologically and chemically. The chemical treatment is generally required for discharge limits less than 1 milligram per liter. Metals used to treat phosphorus are alum, iron, and calcium. Phosphorus is typically tested in the form of orthophosphate and total phosphorus. Again, you want to make sure the units you're talking about, total phosphate requires a digestion. Next. So some future concerns, cyanotoxins, emanating from blue-green algae, pharmaceuticals in our water, selenium, and arsenic. So I'd like to acknowledge the following for their help and for helping me with this presentation. Black & Veatch Engineering, specifically Ed Kobolinski, wealth of information. CDM Smith Engineering, Johnson County Environmental Department, and Johnson County Wastewater. Hawk, Russ Wright with the Blaco University Engineering Series. He has some excellent videos on YouTube. And Scott Hargett, who was our analyst in most of these pictures with Brentech Mid-South.
Well, Scott, I'd like to thank you. There were a few, or excuse me, Sean, I'd like to thank you. There were a few questions that came up during the presentation. If we got a few extra minutes here, let's see if we can answer these. Question number one: Are there other treatment technologies available?
Yes, there's other treatment technologies. There's some actual physical treatment technologies. People are using membrane filtration. I also, within the last 2 weeks, received an email talking about I believe a chemical treatment technology. So with the nutrient limits coming, I'm sure that people are going to be developing treatment for phosphorus and nitrogen.
Okay, and then another question. Is aluminum or iron a better choice for chemical treatment?
That's going to, depend on what the plant is doing. As I said before, if a plant has ultraviolet UV disinfection, then iron is probably not going to be recommended. It can interfere with the transmittance of the UV lamps. So obviously another consideration is the cost of the chemicals. Iron also acts as an excellent sludge conditioner when people are dewatering. I think it's favored if, in the biosolids, like if people are making Class A biosolids, iron is probably preferable. Whereas, alum doesn't really help with conditioning of sludge. But, alum will also run through your system and really, not cause any issues with like UV, even with struvite formation. That can happen because of iron in the system.
And then one last one. The question is, do phosphates used in drinking water for corrosion and scale control contribute to phosphorus in wastewater?
Kevin, I don't think anybody's really, taken a look at that to see if that's, if you can determine that. I know that whenever you're feeding a phosphate in drinking water for scale or for corrosion control, typically, there's a recommended feed amount. You'll measure a residual out in your distribution system just to make sure that you don't have excess. So, hopefully that wouldn't be a cause of concern if, I believe if you're treating properly in your distribution system for drinking water.
All right, well, thank you. I'm going to switch to the last slide here, and I'll leave it up for a few minutes. Again, we have been recording this, so this will be available in video form. It will take a few days before that is up and ready. With the holidays, it may take a little longer than normal. But there is my email address on the very bottom, kcope@brentag.com. Please feel free to email me if you would like a PDF version of Sean's presentation and or a video link for the presentation. So I'd like to thank everyone for attending our webinar today. We look forward to continuing to do this series in the future for you. And again, thank you very much. And with that, we will conclude today's presentation. Again, thank you.